So the next speaker and the last one for this session for the afternoon is Pacaud Lemay with Tensor restriction categories. Take the stage whenever you're ready.
Okay, hi. My name is JS, and today I'll be talking to you about tensor restriction categories. And so this is joint work with Chris Hunan. And so here's a picture of me and Chris running together this past spring. And this is based on our paper also called Tensor Restriction Categories, which is now in TAC, but also on the archive if you want to check it out. So just a bit of motivation for today. Tensor topology, which shouldn't be confused with monodal topology, which Walter Towan will talk about in his talk, is a relatively new area of research, which started in this paper by Enrique Moliner, Hunan, and Tull, where it's based around the idea that monodal categories have an intrinsic notion of space, which is encoded by the tensor product. And so the base open spaces correspond to subunits, which are subobjects of the monodal unit. And one can study concepts of partiality, restriction, support, etc., with respect to these base spaces and the induced spatial structure. But of course, there's also another dimension to monodal categories that doesn't deal with the tensor product, and which is instead deals with composition. And the way we talk about partiality with respect to composition is captured by Cochran and Lack's restriction categories. And so restriction categories give the ability to handle maps that are partially defined with respect to composition. And so today's story is to bring these two notions of partiality together. And the way we did this is by introducing a construction which we call the S construction, which turns a monodal category into a restriction category, where the restriction structure is induced by the subunits. So what I'll do in this talk is I'll also discuss restriction idempotence, tautomorphisms, restriction isomorphisms in this new S construction. And at the very end, I'll briefly talk about how we characterize restriction categories of the specific form, which we will call tensor restriction categories. So I'll start off by discussing the definition of subunits. So throughout my talk, I'll be using the graphical calculus for monodal categories, and my string diagrams in this talk and in our paper are to be read from bottom to top. So a subunit in a monodal category is a subobject of the monodal unit. So in particular, this little s, this map little s is monic, and I'll draw them as so in the graphical calculus, such that little s tensor the identity is invertible. And so in particular, what this means is that S is isomorphic to S tensor S. And so we draw these inverses as follows. So in particular, the inverse on the right, you can think of it as a kind of copy map. And we'll see in a few slides how subunits correspond to this idea of open spaces. Now, subunits are well behaved in a firm monodal category. So a braided monodal category is firm when I take two subunits, S and T, well, little s tensor the identity of T is also going to be monic. And then we have a cool result that says that in a firm monodal category, the subunits form a semilattice, where the meet of subunits is defined using the tensor product. And the top element is the monodal unit. The induced order for subunits is precisely the induced order of subobjects. So here are the examples that we'll consider today. So if X is a locale with frame of opens O of X and top element T, then the category of sheaves of X is a firm monodal category, where the tensor product is given by just the finite product structure. The subunits correspond to the subterminal sheaves. So the way these are defined is that if I give you an open U, then the subterminal sheaf associated to U, called chi of U, is the one where if V is less than or equal to U, then chi of V is just the singleton. And if not, chi of V is the empty set. And so in this case, because the subunits correspond to the subterminal sheaves, then the semilattice of subunits is precisely just the frame of opens. Another nice example is that I can take any semilattice L and make it into a ferminodal category where the tensor product's the meat and the top element and the monodal unit's the top element. In this case, every element is a subunit. I can also take another example is the category of sets, where again, the monodal structure is given by the Cartesian product. And the subunits in this case are just the empty set and the singletons. If R is a commutative ring, then the category of modules over R is also a ferminodal category. And the subunits are the idempotent ideals of R. So these are idempotents J, such that J is equal to J squared. But now I want to talk about the other side of the story that we want to bring together, and this is restriction categories. So a restriction category is a category which comes equipped with a restriction operator. So what that is that for every map from A to B, there is an associated map F bar from A to A, which captures the domain of definition of F and satisfies 4 axioms that I wrote down here. And F bar is called the restriction of F. So the canonical example of restriction category is the category of sets and partial functions, just called par, where for a partial function F, F bar is defined as follows. So F bar at X is equal to F if F of X is defined, while F bar of X is undefined if F of X is undefined. So now I'm going to introduce the S construction, which essentially starts with a ferminodal category and will produce a restriction category via the subunits. So how does this work? So start with a ferminodal category C, define S of C as follows. So S of C has the same objects as C, but the maps in S of C, so a map from A to B in S of C is going to be an equivalence class, which I'll just write like this, little s followed by F, where it's an equivalence class of pairs where the first component is a subunit, and the second component is a morphism of type A tensor the subunit to B, where 2 pairs are identified if there's an isomorphism between the subunits such that which are compatible with the maps in the second component. And so I'll use the graphical calculus to draw out maps in S of C as follows. The identity morphism is are those where you take the subunit to be the monodal unit and just the identity on the object A. And then composition is defined using the meat of subunits. So on the subunit part, you take their meat. And because remember that the meat of 2 subunits is given by S tensor T, then I can just compose F and G to get a map of the appropriate type. And so this gives us a restriction category. So S of C is a restriction category where bar of SF is equal to, well, you don't do anything to the subunit, but you replace F by just taking A tensored with the subunit map. And this does give a restriction category, and the restriction axioms hold essentially because subunits are idempotent. So here are some examples. So if I start with my category of sheaves, well, for an open U, let's define the restriction of a sheaf F restricted to U as follows. So if V is less than or equal to U, then F restricted to U is just F at V. And if not, F restricted to U is just going to give the empty set. So S of the category of sheaves can be described as the category whose objects are sheaves and whose morphisms are pairs consisting of an open and a natural transformation between the restriction of the sheaves at that open. If L is a semilattice, then the Hom set SL between 2 elements of the semilattice is equal to all the elements of the semilattice such that X meet S is less than or equal to Y. And so in a certain sense, S of L approximates the free Heighton algebra over the semilattice L. And this is closely related, and what's cool is that we found out that this is closely related to the work by Ball, Pulcher, and Weiland in their paper, in this paper of theirs. Another neat example is that if I take S of set, then this is actually the free category over set with 0 morphisms. And the way you can see this is that the Hom set S of set between two sets X and Y is just isomorphic to the Hom set between X and Y in set plus an added on distinguished element. For the category of modules over a ring, there's not much we can say other than the fact that the morphisms capture this notion of recording an ideal in the domain of definition of the morphism F. So now I'll start talking about the various notions of restriction structure. So I'll start with restriction idempotency. So a restriction idempotent in a restriction category is an endomorphism such that E is equal to E bar. So it's equal to its own restriction. And so for an object A, write O of A for the semilattice of all restriction idempotents of type A. And the important thing is that for every morphism F, F bar is a restriction idempotent. So in our canonical example, in par, the restriction idempotence of X corresponds precisely to its subsets. So in this case, O of X is isomorphic to the power set of X. But for the S construction, it's a bit different. So the restriction idempotents in S of C are precisely those of this form where it's just a subunit, but where the map is just A tensored with the subunit map. And so this means that for every object A, I have a semilattice isomorphism between O of A and the semilattice of subunits of C. Another important class of maps in a restriction category are the total maps. So these are the morphisms that are defined, that are completely defined. So a total morphism is a map from A to B such that F bar is just equal to the identity. And the subcategory of all total morphisms of restriction category X, I'll just denote T of X. So in par, the total morphisms are precisely the total functions in the classical sense. So you have that T of par is just equal to the category of sets. For a firm monodal category, a morphism is total if and only if it's of the form the monodal unit followed by just some morphism F from A to B and C. And so this induces an isomorphism T of S of C. This induces an isomorphism where the total maps of S of C recaptures the base space. Sorry, I thought we started late. Just some.
And I apologize. How much time do you need for this?
I mean, I can finish up, but maybe a bit more than 5 minutes, but that's fine.
Yeah, that's fine.
Okay. So just moving forward. So in a restriction category, we also have this notion of restriction isomorphism. So these are like isomorphisms, but where instead, so F is a restriction isomorphism if there's also a map F circle, such that when I compose F and F circle together, I don't get the identity, but I instead get their respective restrictions. So in par, F is a restriction isomorphism if and only if it's a bijection where it's defined. And for the S construction, it turns out that restriction isomorphisms essentially correspond to isomorphisms in the base category. So this morphism here is a restriction isomorphism if and only if, when I precompose it with that copy map from my very first slide, I get an isomorphism down in the base category. And what's neat, and I won't say much about it, but using these restriction isomorphisms and the total morphisms, we actually get an orthogonal factorization system on S of C. So I guess, so the last part that I want to talk about is just this idea of characterizing the restriction categories, which are the form S blank. So a tensor restriction category is going to be a firm monodal category such that it's also a monodal restriction category. So this means that it's a restriction category where the restriction operator is compatible with the tensor product. And it also satisfies 7 axioms, which essentially demand that a notion from a restriction category agrees with its corresponding notion from tensor topology. So here are 2 examples. First of all, that restriction idempotency on the monodal unit correspond precisely to subunits via the fact that there's always going to, that for every subunit S, there's a map going from the monodal unit to S. And that this implies that restriction idempotency on A also correspond to subunits via this construction here. But also there are axioms which gives us a factorization system in the sense that every map F can be decomposed into a restriction part, which involves a subunit, and a total map and a total map associated to F. So then we have this nice result that says that for any firm monodal category C, S of C is a tensor restriction category. And that conversely, if X is a tensor restriction category, then T of X is a firm monodal category, and X is actually isomorphic to S of the total morphisms of X. However, we have to stress that not every firm monodal restriction category is a tensor restriction category. So in particular, the canonical example of restriction category is not. So this is because recall that T of par is equal to set. But remember that S of set is just S, the hump set S of set between X and Y is just set X, the hump set in set of X and Y plus a distinguished element. But of course, there are many more partial functions than just the total functions plus one extra thing. So clearly, par is not equivalent to S of the total maps of par. So par is not a tensor restriction category. So I think the very last thing I want to say from a theory point of view is that the S construction also gives us this notion of co-restriction and range. So S of C is a co-restriction category. So it's also which is just the dual of a restriction category, where the co-restriction operator just takes a map S and F and spits out essentially the same thing as the restriction. But you'll notice that while the restriction gave me A, the co-restriction gives me the codomain of F, so the B part. And this also makes SFC into a range category. So range categories are like restriction categories, but where you axiomatize this notion of the image of a function. And so Chris and I conjectured at the end of our paper that it is possible to axiomatize tensor restriction categories in terms of co-restriction categories and range categories, but we figured that this might be a story for another time. Okay, so I guess I ended up finishing in 5 minutes anyways. So just to conclude, tensor topology thus gives us new sources of examples of restriction categories. Restriction categories are relatively more established. So while tensor topology is relatively more recent, so one hopes that the techniques from restriction category theory can be useful and applied to tensor topology. But also it'd be cool to see if we can adapt sort of a graphical calculus for subunits and tensor restriction categories in the same way that there's a string diagrams for Cartesian restriction categories. And the last thing I want to point out is that recently, Chris and his co-authors have instead started to work with this notion of central idempotents, which are like subunits, but drops this the component of being monic or a subobject. So it would be interesting to work out how far we get in the restriction story with central idempotents instead of subunits. And so, yeah, that's all from me. Thanks for listening and merci.
Okay, thank you very much for your talk. And now we have time for questions. Do we have questions in the room? Yes. One has a question.
Right. So my question is sort of starts with the observation that as restriction categories, from this perspective, being a restriction category and a co-restriction category, and the way that it's a very sort of degenerate example. And it seems to me that you might compare it to something like the Cartesian product of like the semi-lattice of subunits sort of suspended as a monoid, and some category of total maps, where so sort of something, a simpler characterization like this of this kind of restriction category. I wonder if you've thought about this from this sort of angle.
Sorry, Chad, I didn't follow your question.
So the restriction structure in the tensor restriction categories is very simple, insofar as the semi-lattice of restriction idempotence at every object is the one of subunits.
Right.
And am I right to think that these sort of the domain of definition part is somehow disconnected from the map part?
Yes. So from this, I guess, in a sense, yes, from this factorization system, but the subunit part is still plays a role into the domain of the total function, right?
I might have to read it, but
okay.
Never mind. I guess my question was if you thought of sort of decomposing it into these two parts.
Oh, yeah, I think we have, but if you go through the axioms, I think the answer is yes to your question.
Oh, okay. Thank you.
Thank you. We have another question from Adrian. Would you unmute him? Okay. Adrian, you are unmuted.
Hello. Thanks for your talk. That was very interesting. I'm wondering if the S construction that you described extends to a two-functor in an interesting way. I mean, with respect to the either lax or collax monodal category morphisms. Yeah.
Yep. So it's a two-functor, and it actually gives an equivalence between tensor restriction categories and firmonodal categories. And also, I can't remember if it's a monad or a comonad, but it's one of those. And then tensor restriction categories are either the algebras or the coalgebras of said monad, comonad. But maybe Chris remembers if it's a monad or a comonad, but we figured that part was maybe too out there for the paper itself. But if you're interested, I'm happy to discuss more about it with you.
Do we have any more questions from the audience? Apparently not, so we thank the speaker one last time. Thank you very much. And before we leave, so the session is over, but don't remember to attend the Q&A session this afternoon from 6 to 7, UTC +2. And the direction are in an email you should have received from the conference organizers. So thanks everybody for joining this session, and see you tomorrow morning. And no, sorry, no, it's not true. See you at the Q&A session. Bye.